Hey, Professor, how are you?
I'm good. How are you doing?
Great. Um, I know I had told you I was sick the other week, but I'm just starting to get back to full strength now. So
Wow,
all
that was
good.
rough.
Yeah, I think what was so scary was it was so random. I don't know if you remember, I told you it was pneumonitis.
Hmm.
Hmm. Nah, it just started off as like a sore throat, and then the next day it transgressed into like immense chest tightness. And even throughout all my like time with asthma, I've never had chest tightness like that ever. So I'm good now. Now I just got like a little bit of brain fog, but I'm starting to like get through it. I didn't test positive for COVID, but I think it was.
Oh,
But they kind of mishandled the testing at the hospital. Like they did one nasal swab and then like 6 hours later, they're like, oh, we got to do it again. We lost the first swab. It's like, what are you doing? So, I mean,
mm.
yeah, so I'm good now though. They had me on like prednisone and some other anti-inflammatory stuff.
I'm glad you're feeling better.
Yeah, me too. It was scary. Just the uncertainty and not knowing what it was. But yeah, I'm great. So
Well, we
how
missed you.
how are you?
I'm doing okay.
How's the weather over there in California today?
Pretty good. I think it's supposed to be sunny and 70.
Okay, that sounds that I'd take that here every day. Are you in like the LA sub area or whereabouts in California are, if you don't mind me asking?
Yeah, we're a little bit north of LA,
Okay, nice.
so not quite to Santa Barbara, but in between the two.
Okay, that's a nice area.
It is.
I
It
have a
is.
friend from the Air Force. He was living in Southgate, but now he's above that like northern LA too. He says he loves it out there. So
Yeah. Yeah, I
just
went to grad school at UCLA, which is in LA, and
yeah.
there's a lot to like about this area. But when I left grad school, when I was done with grad school, I was like, I'm never going to live in LA again because
Yeah.
the traffic is just such a nightmare.
Oh, I can imagine too.
Yeah, today, um, one of the most one of the biggest highways in LA is shut down at an area where there's not really another way to get through that area from
Yeah.
one part of the city to another.
Was it for like infrastructure repairs or just a crash or what?
Officer involved shooting.
Um,
So yeah, that's Juliana. You have your hand up?
Oh, I was just gonna say that I actually used to live in West Hollywood, and I know around like the UCLA area, the homeless population is like really bad. Like that was what I didn't really love about LA was the homeless population. It's really like a dramatic, eye-opening experience seeing that.
Yeah, it's gotten worse since I was out here in grad school. It's really bad. And it's frustrating because the kinds of solutions that the government is proposing are not compassionate solutions. And I'm like, you're not solving the problem.
yeah, it's sad.
Look at the cause of homelessness and fix that problem. Don't just
They gotta find a way to lift these people up, like work with them, help them get employment, develop life skills, help them combat drug addiction. I mean, I
yeah.
used to be of the mindset that it was, oh, these people, they have issues, it's their problems. But part of that's true, but we also have to work with these people and help them become prosperous because if we help these people, then they can help us as a society. So
Yeah. Yeah.
definitely multifaceted, and it's not as simple as, oh, they're lazy or oh, they don't want to work or they're this or they're that. Like it
Yep.
took a while for me to realize that, but when you see it firsthand, it helps drive that home. So
Yep.
but
And
we talk about that all day. But
yeah. That's not
virus.
epidemics. We gotta
Well,
get started.
this is an epidemic, but
Oh,
not
okay, that's true, it is.
yeah.
But it's not one that I've got scheduled.
Here.
All right. So okay, hang on, who just showed up? Okay. All right, so let's go ahead and get started. There is some stuff due Sunday, the review quiz and essay number 3, both due before midnight on Sunday. And the project is going to be due, oh, and there's Jerry. Midnight on Sunday, May 1st. If you're doing a presentation, you're going to be doing it either on the 26th or the 28th. I've only had one person say they have a specific day they want, but if you want a specific day, there's still some flexibility. Otherwise, I'll use a random number generator to figure out who goes which day. Any questions on the project?
I had a question on the essay,
Okay,
if that's okay. So I wanted to do the first prompt about like what we can learn from ancient pandemics, but I was wondering if I could just augment slightly the topic. Well, I do want to stick to like lessons learned, but I kind of wanted to implement like what we've learned from not so ancient pandemics and how we can use that moving forward. I still talk about the Neolithic decline in there, but I kind of wanted to focus on how we learned the importance of variolation and how inoculation helps, how we learned about masking in the 1918 flu. And I just was wondering if that was okay with you.
yeah, that's okay.
Okay, thanks.
Yep. All right, so I updated the schedule a little bit here. So I wanted to post this. It's just a little bit tweaked, but this is the entire rest of the semester, guys. We are almost at the end of the semester. So I anticipate that we're going to talk about malaria next week. And the week of the presentations, a little bit about bioterrorism, which is using infectious diseases for terrorist purposes. We've mentioned it a little bit, but I'm going to give you some more recent examples. And then the last week, I want to spend some time talking about post-viral syndromes. So it turns out that just getting over a virus doesn't always mean that it's done with you so much. So we know about long COVID now, but there's also, like HPV can cause cancer years down the road. And I want to mention a little bit about Lyme disease and the long-term situation there. And there was a recent discovery that past exposure to Epstein-Barr virus is related to muscular dystrophy. So I want to talk about a couple of those things that last week. All right. So we're talking about malaria. And last time we were kind of going through all of the things that malaria can do to your body. And we were starting to mention how it can evade the immune system. So I had mentioned that it can, because it has all these different forms, each form of the parasite requires a different immune response. Remember, the immune system targets specific proteins. And the different forms of the malaria parasite have different proteins on the surface. So if your body recognizes, let's say, the form that infects the liver, it'll go after that one, but the form that infects the red blood cells looks to your immune system like a completely different disease, and it doesn't recognize it. It can also hide in the liver cells. So when it's infecting the liver cells, it's very, very hard for the immune system to find it there. It makes changes to the red blood cells to kind of reduce the ability of the immune system to see that that cell is infected. So in general, when a cell is infected, it puts an antigen on the surface. You guys remember antigens? What are antigens? Ooh, lost that memory there.
Isn't it when it's an outside substance that when it gets introduced to your body, it creates a response?
Yes. I'm gonna say usually an outside substance, often a protein that causes an immune response. I say usually outside. Nate, go ahead.
Is that called an innate immune response? Because I know you've used that term before, and I think the term innate means new or novel or like an initial response to something.
Yes.
Okay.
Yes, but if your body has seen that antigen before, then it activates the memory cells, and that's not the initial innate immune response.
Right. So innate is restricted to only something that the body hasn't experienced before.
Yes.
Okay. Thank you.
You're welcome. All right. Now, I said usually an outside substance because, as I was saying, cells in your body can put an antigen on the surface, a protein that says, hey, there's a problem here. That's an inside substance. That is something that your body produces. So those are just to signal that there's an infection. And of course, things can go wrong. And the immune system can respond to normal proteins that should not be antigens. And these are autoimmune disease. Lupus, Crohn's disease, rheumatoid arthritis, multiple sclerosis. There's a whole bunch of these. Type 1 diabetes can sometimes be caused by autoimmune disease. Okay, so normally your cell gets infected, it puts the antigen on the surface, and your immune system goes after it. But malaria prevents the red blood cells from being able to do that. So the red blood cells cannot signal that they're infected. Now, the red blood cells will get an antigen on the surface from malaria infection. This is a malaria protein. And here's the tricky bit. Malaria can change proteins that it produces. These antigens that come from the malaria parasite, malaria can change and produce a different protein. Nate, go ahead.
Is that related to how the malaria actually has several transformations and each transformation can produce a different antigen, or am I just grasping at straws here?
I wouldn't say you're grasping at straws because the different forms do have different antigens, but this is a different trick. So it's one form that has different antigens. So imagine if you work for the FBI and you're on the hunt for a serial killer, and the serial killer always wears a Bill Clinton mask when he kills people. But then you spread the word, avoid people wearing a Bill Clinton mask. And he starts wearing a Barack Obama mask. Now, we're smart enough to recognize that wearing a mask is wearing a mask. Your immune system isn't. And it will say, oh, that's Barack Obama. That's not the serial killer. And so malaria is constantly changing that, the way it presents itself to the world. It's changing its mask. It's changing its appearance frequently. So the immune system learns to recognize the one antigen from malaria, and malaria then produces a different antigen. It's not the only parasite that does this. This is a common tactic that parasites use to evade the immune system. Okay, so these are the kinds of things that it can do to evade the immune response. So if you want a screenshot of this, this is a good time for a screenshot. Okay. So if you are sick, you've got the symptoms of malaria, this cyclical fever, this fever that comes and goes at regular time intervals, they're going to try, the doctors are going to try and diagnose you. Well, diagnosis of malaria is difficult. And it is done by microscopic examination of blood. So literally, somebody gets your blood cells, stains them, and looks at them under their microscope to see if they are infected. And what they're looking for are these little structures here. So you can see it kind of looks like a ring with a darker staining, one or two darker staining circles. This is an excellent image of malaria infected cells. So this one, this one, this one, this one. This is a white blood cell, white blood cell, white blood cell. The others are red blood cells. How many infected cells do you see in this picture?
8.
The top or the bottom?
The bottom picture.
3, 4, 6, 8, 9. One all the way to the left.
Yep, so there's one here, 1, 2, 1, 2, 3, and these are white blood cells.
Oh, okay.
Yeah.
So it doesn't attack white blood cells, only the red ones?
Just the red ones.
Okay. Does that have to do with the red blood cells carrying oxygen or hemoglobin or something like that?
Yeah, it's the hemoglobin. They actually, the parasite actually consumes hemoglobin. That's what it uses as a food source. So you can imagine that if somebody has a low parasite load, that it can be tricky to find these cells under the microscope. I've looked at slides of infected blood cells before, and usually the blood cells that they use have been artificially infected, so you have a very high infection rate. When you get blood straight from a person, there might only be 1 or 2 of these on a whole slide. And so you're spending half an hour looking through the slide, looking for one of these, if you got one at all. So it's very, very difficult. It depends on the skill of the person looking at the slide and their patience. But it's cheap, right? Microscope slides are relatively cheap. You just got to pay somebody to sit there and look at the slides. There are some other tests that have been coming down the pike, but they're expensive. And malaria is a disease that occurs in more impoverished parts of the world. It's not occurring in the wealthy nations like Europe and America. Nate, go ahead.
Does any of that have to do with just where mosquitoes are more abundant? Because I mean, well, I'll just say it. I know there's a heavy mosquito population in like Africa and sub-Saharan. So I'm sure that only compounds and amplitudes the infections, right?
Yes, it does have something to do with mosquito populations as well as the specific species of mosquito. And we're going to talk about that in a little bit because there's a bit of a backstory there. Yeah, India, Central, South America, Sub-Saharan Africa, those are the kinds of places we tend to see malaria nowadays. Okay. Treatment. Well, remember, I told you there are 4 different parasites. So it depends on which parasite a patient is infected with. So you can't treat malaria the same if it's malaria Plasmodium falciparum versus Plasmodium ovale. The different strains have different treatments. Where the person was infected can sometimes help figure out the species. So different species usually occur in different places. But there is some overlap, so that doesn't always work. Where a person was infected can also tell you if there is a possibility of drug resistance. Just like how some bacteria have become resistant to antibiotics, some malaria parasites are resistant to the drugs that we use to treat malaria. If we're talking about Plasmodium falciparum, generally speaking, hospitalization will be required because that is the deadly strain. That's the most deadly strain. Other than that, a lot of it depends on the clinical status of the patient How severe are the symptoms? Less severe cases can be treated with oral medications. More severe cases, we're going to use intravenous. So we're going to do injections. Nate, go ahead.
This was kind of just a general question, but based on like what you've seen and your knowledge in terms of treatment, would you say that pathogens derived from parasites are usually the most difficult or troublesome to treat?
Yes. Yes. Parasites are definitely more difficult to treat than any of the other categories. Fungus, which we don't tend to get bad fungal diseases. But if you do get a bad fungal disease, that's harder to treat than a virus or a bacteria.
There's like a fungal pneumonia too, right? I
Yes,
think
there
you
is.
were talking about that. Yeah, that sounds scary.
Aspergillosis. Yep. So in addition to how severely sick the patient is, has the patient used anti-malarials before? Because if they have, they're more likely to have an anti-malarial resistant strain. This includes when it's used prophylactically. You guys know what prophylactically means, or prophylaxis?
Post-exposure.
No, not post.
Pre-exposure, sorry.
Pre-exposure. So as a preventative. And of course, you know, the age and general health of the patient are important here too. All right. Screenshot time. So oftentimes a mix of different drugs is used. This reduces the risk of resistance. As a parasite that's resistant to one drug is less likely to be resistant to other drugs. Having resistance to multiple different drugs is harder, evolutionarily speaking, and it's harder for the organism to sustain it, because usually anything that produces resistance to a medication is not so good for the organism. A lot of times organisms that are resistant to treatment are not as vigorous. They don't grow as fast. And that kind of stuff can happen. Now, here's some of the problems. Anti-malarial drugs have a lot of side effects. So, nausea, vomiting, abdominal pain, skin rash, which doesn't sound bad, but it can be bad. Headache, insomnia, dizziness, and here's the weird one, vivid dreaming. And by vivid dreaming, it's generally nightmares. That's just such a weird side effect, but it is one. So, you know, if we've probably all taken antibiotics, and you get a little bit of an upset stomach, maybe a little bit of diarrhea. This is worse than that. This is like having a stomach bug. So you're vomiting, you've got diarrhea coming out the other end, everything hurts, you can't sleep, your head hurts. When you do sleep, you have nightmares that wake you up. Not fun to be on these medications. And when we talk about prophylaxis, taking medication to prevent getting malaria. These are commonly prescribed for people going to certain parts of the world. Now, here's the problem. A lot of the anti-malarials are the same medications that are given as a preventative. So you can get the same side effects as if you were being treated. So my first trip to Africa, I was with a group of, how many of us were there? 15, 16 people. We were all relatively inexperienced at traveling to Africa. We'd all gone to a travel doctor who'd given us medication to take to prevent malaria. I got the skin rash, and it was nasty, really nasty rash. So I immediately quit taking the drug. Other people in the group had the insomnia, the headaches, the vivid dreaming. By the time the trip was over, none of us were still taking our anti-malarial prophylaxis. None of us were. The side effects were just too severe. Well, that increases the risk of resistance showing up. So if any of us had gotten infected, it was more likely that that parasite would develop resistance to the anti-malarials. It can be hard to determine the risk when you are traveling. So I've been to Africa multiple times now. I've been to Central and South America multiple times. And I've learned that if you just go and you look at the State Department's traveler advisory website, they will say, oh, you're going to Tanzania, you need to take anti-malarial medications. But it may be that malaria is only present in certain parts of the country. And it may be that the malaria is only present seasonally. So if you don't know the area very well, you look at the advice from the US government and you think, well, I guess I should take prophylaxis, but sometimes it's completely unnecessary. Nate, go ahead.
This is kind of just speculation, but how beneficial would it be to just wear like a constant like beekeeper suit or something like that so you never get the risk of being bitten? I mean, I'd rather do that than take these pills, to be honest.
Absolutely. Yes, there are bug suits, not so much a beekeeper's uniform, but there are hats that have mosquito nets that cover your head and neck, long sleeves, long pants, gloves. I mean, they get hot. That's the problem. And usually when places that have nasty malaria are hot, so hot is an issue. But fortunately, the mosquitoes that carry malaria tend to be nocturnal. So mosquito bed nets are a much, much better solution. So every time I travel to an area with malaria, I purchase a mosquito bed net, I use it, and I generally leave it because for me to purchase a $20 mosquito bed net, that's not a big deal. But for a lot of these places where I tend to travel, the local community, that's a lot of money for them. And it can be hard to afford or get a mosquito bed net. So I strongly recommend those if you're traveling to malaria prone areas. Okay, questions on this part?
So Professor, you were saying that fungi are the most difficult to contend with of virus, bacteria, and fungus group.
Yes.
So is that why the flesh-eating disease is really a hard thing for people to deal with?
I thought that was a bacteria.
Oh, cheers, you're right. It's not a fungus.
Isn't there like brain eating amoebas and like stuff like that too?
Brain-eating amoebas are parasites,
Oh, okay.
which are harder than fungus to deal with. Yeah.
So what is a fungus that people get infected with or
Okay. The ones that you've heard of don't cause a lot of problems. Jock itch, athlete's foot, yeast infections.
Oh, okay.
Those are all fungus. In fact, they're all
Okay.
the same fungus.
Oh, really?
Yeah. Ringworm. People can get ringworm. That's hard to get rid of.
I remember that as a child. I remember seeing people getting their head shaved and it's like their head would be a little ashy. I'm like, what's going on here? Oh, I had ringworm.
Yeah. Yeah.
Weird to call a fungus a worm, isn't it?
Yeah,
'Cause
I
just
thought it was a
infect-
worm as a kid.
Yeah, I thought it was a
they were
parasite too. Yeah.
gross.
No. The dangerous ones tend to be things like aspergillosis or psittacosis, which you probably have never heard of before. And I'm pretty sure there's a disease called valley fever. I'm pretty sure that one is fungal as well. And again, it gets in the lungs and can be really nasty.
That second one you mentioned, aspergill. I know that prefix asper is common in like fungus species. So yeah, aspergillosis.
Yep. Yeah, that refers to the specific strain of fungus that causes the problem. Anything else before we go on? Okay. Got your screenshots? All right. So malaria. Nowadays, malaria occurs in all of these slightly colored areas, and the darker the area, the more cases of malaria per 1,000 members of the population. At risk. This is a key word here, or a key phrase here, because if you get malaria and you recover, you are more resistant to reinfection. Now, you do have to get full immunity, you do end up having to get infected multiple times, which is not good. But the more times you get infected, the less severe the symptoms are going to be, the more likely you are to survive. This is why most of the deaths occur in children under 5, because it's their first infection with malaria. And resistance is not lifelong. So say you come from this part of Africa, you got exposed to malaria a bunch of times as kids, you've got some immune response, and you move to Massachusetts. You're not getting exposed to malaria anymore. 20 years later, you go home, bam, you can get malaria again. Your resistance is gone. Now, there are genetic forms of resistance. We're going to talk about those in a little bit. So there are some genetic characteristics of people that confer resistance. But you can see most cases of malaria are occurring in sub-Saharan Africa, some in South America, a little bit in Central America, a little bit in China, some in India, over here in Indonesia and New Guinea and that sort of the world. So we don't see it in the US, we don't see it in Europe, we don't see it in Australia. This is where malaria originally evolved, to infect humans. So remember, malaria is an ancient disease. It's been infecting humans since there became humans. So it evolved to infect humans as humans evolved in Africa. Hey, go ahead.
And you said at one point it was an algae, or it's derived from algae. It had genetic markers for photosynthesis.
Yes, that was, it was probably an algae maybe 200 million years ago. So it's been a very, very long time, but we can tell because some of the genes it has nowadays are clearly derived from algae genes. Yes.
So it predates humans then, right?
Yes.
Okay.
It predates dinosaurs. Okay. So, not surprisingly, as humans started to do agriculture and formed larger communities, that favored the spread of human-specific malaria. So many diseases benefit from us living in tighter communities and from us developing agriculture. So before we had agriculture, before we had long distance trade, a disease could come in, infect a community, wipe out that entire community or most of the community, and then have nowhere to go. So it could potentially just, wipe out a community and then disappear from the face of the earth. It probably happened lots and lots of times before we started having agriculture. Once we had agriculture, we started trading and traveling. Now we're spreading these diseases and they're sticking with us. So early in the history of malaria, the strain or the species Plasmodium vivax was the most common strain originally. Now, a genetic mutation arose in humans that provided protection against vivax. You may have heard about this, probably not. This is called the Duffy antigen. More accurately, it is the absence of this antigen. So the Duffy antigen is a protein that normally occurs on the surface of red blood cells. And it is used by P. vivax to enter red blood cells. So not having this antigen on the surface of the red blood cell meant that people who are missing this cannot be infected with Plasmodium vivax. It can't get into the red blood cells. By about 5,000 years ago, almost everyone in Africa lacked the Duffy antigen. Even today, 90% of people with a significant percentage of African ancestry do not have the Duffy antigen and cannot be infected by Plasmodium vivax. Okay, this is great, right? Go ahead and take a screenshot. What do you think happened?
The parasite mutated.
Yes, parasite evolved, and it evolved into falciparum strain, which is the more deadly form. This species probably requires a larger population to persist. So a small population means that it's not going to persist. Vivax, remember, has a dormant phase. So it doesn't need as large of a population because it can survive with lower population density because it can hang out in the liver cells long term. Now, when we have, when we see falciparum, it has a higher case fatality rate. It is better at evading the immune system than Vivax. It can change the antigens, like I was talking about earlier. Each new generation uses a different antigen or disguise, to disguise from themselves from the immune system. This bypasses the acquired or adaptive phase of the immune response, the part that remembers. All right. But again, the more times you get exposed, the more likely you've been exposed to all of the different antigens it can produce, and the more likely your immune system will recognize it. There's not an infinite number of options for the antigen here. The high death rate caused humans to evolve resistance, right? So we start getting some resistance showing up. These, Nate, go ahead.
That's just literal natural selection, right? Like the textbook definition of it.
Yes.
It's like we're in a competition for our DNA to evolve faster than their DNA to evolve.
Yep, it's an arms race. Now, the mutations that provide resistance to infection with Plasmodium falciparum tend to have some sickness and mortality associated with them. So if Plasmodium falciparum disappeared from the planet, these genes would probably disappear pretty quick. because people who have this mutation are more likely to have health problems and possibly even die early. Despite that fact, 1 out of every 14 people has a mutation that provides resistance to the falciparum form of malaria worldwide. 1 out of 14, everybody. They are definitely more common with African ancestry. All right, so I'm going to talk about one. If you guys want to get a screenshot, I'm going to go back and we're going to look at pictures again. All right, so there are 3 major conditions that confer resistance to malaria. Thalassemia, which is a form of anemia. G6PD, I'm going to explain that a little bit later, but that's involved in cell energy management. Sickle cell anemia is the most common one. So this is sickle cell anemia here. So you see these curved red blood cells. That is not normal. A normal red blood cell looks like this. Little kind of donut looking, a little bit paler in the center. This is a sickle cell. So when we talk about sickle cell anemia, the gene that causes this causes the red blood cells to be an abnormal shape, which means that instead of moving smoothly through the small blood vessels, these abnormal shaped cells can get stuck. They can clump up and cause clots inside of blood vessels. Not good. So I want to cover the genetics first. If you've had simple genetics, you may have learned the genetics of sickle cell anemia, right? Everybody has 2 copies of each gene. Sickle cell is a form of one of the hemoglobin genes. Hemoglobin is the molecule in your red blood cells that actually carries oxygen. Now, 1 copy of sickle cell and 1 normal hemoglobin provides resistance to malaria with relatively few side effects. A lot of people who have this condition, we call them carriers, don't even know about it. Nate, go ahead.
That term for the mutated gene, that's called an allele, right?
Yes.
Okay.
Each version of the same gene is an allele. Absolutely. It's like having different recipes to make cookies. You're still making cookies. So if there are 2 copies of the sickle cell version or allele, without modern medical care, this is often fatal. So I'm sure you guys have seen Punnett squares before. So if we look at this family tree and we have 2 parents who are both sickle cell carriers. So they've got 1 normal hemoglobin gene and 1 sickle cell version of the gene. When you produce sperm and eggs, you only put 1 copy of each gene in each sperm or egg. So the guy here can produce sperm that either have the normal hemoglobin gene, or he can produce sperm that have the sickle cell version of the gene. Same thing with the woman. She's a carrier, so she can either produce an egg with the hemoglobin, the normal hemoglobin version, or she can produce egg with the sickle cell version. If the offspring gets a sperm with a normal hemoglobin and an egg with the normal hemoglobin, both copies of their genes are going to be normal hemoglobin. They have no sickle cell gene. They are healthy, but have no resistance to malaria. Didn't leave enough space for more words. If instead they inherit the sickle cell version of the gene from dad and the normal hemoglobin from mom, they are a carrier and they have resistance to infection from malaria.
I think I asked that last week, that is malaria, is it hard for people with sickle cell to get malaria?
It is. Yep.
Oh.
I think I told you you had to wait a week.
Oh, that's what you said. Yeah.
If the offspring gets the sickle cell version from mom and from dad, they have sickle cell anemia. Anemia. All right.
So this may sound kind of morbid, but if you have 1 sickle cell gene, it actually is beneficial to malaria. I mean, I know it's a slight like occurrence or whatever, but
You're getting right to the point. Even though before modern medicine, each child a pair of carriers had a 25% chance of dying in childhood, the gene malaria is so deadly that these individuals would still have a reproductive advantage. So
was sickle cell originally a mutation to combat malaria, or?
Well, we don't develop mutations because we need them. So sickle cell just kind of showed up at random, but because it conferred resistance to malaria, that's why it still persists. That's why it became so relatively widespread? Because in the presence of Plasmodium falciparum, losing 1/4 of your children to sickle cell, but having half of your children have resistance means more of your offspring will survive and reproduce. If you didn't have the sickle cell gene, you would lose more children to malaria than you would lose if you are a carrier.
And obviously, this is just a small sample size regarding where malaria is abundant. Like, it wouldn't really be beneficial if you were in Russia and you had one sickles. Yeah, okay.
Yeah, yeah, yeah. If you aren't around this, and it's this strain of malaria, the other strains are not as deadly. But if you are around Plasmodium falciparum, absolutely, it's an advantage. If you aren't, sickle cell allele is a disadvantage because you're likely to lose 1 out of every 4 of your children. So in areas that have this particular parasite, the falciparum parasite, about 40% of the population are carriers. Okay. All right, good time for a screenshot. All right, so how does sickle cell confer resistance? What is it doing that allows people with this allele, this version of the gene, to be resistant to malaria? One of the biggest things that happens is sickle cell red blood cells. So if you're a carrier, some of your cells are going to be sickle cell. Some are going to be normal. The ones that have the sickle shape have a shorter lifespan than normal red blood cells. And so what happens is you have fewer total red blood cells. That's part of it. And if a parasite, the parasite requires a relatively long time in the red blood cell to reproduce. So if your red blood cell ages out and dies of old age and it's infected, the parasite will get removed from the body. It's not going to be able to go on and infect more. So if your red blood cells aren't living as long, the parasite doesn't have the opportunity to reproduce. If it infects a sickle cell red blood cell, it's not going to have enough time to reproduce. That means that your total parasite load will be lower. Parasite load meaning the number of parasites in your body. And that gives your immune system a better chance of clearing or getting rid of all of that parasite. All right, so sickle cell is the best known and most widespread genetic form of resistance to malaria. Are there any questions on this one? Okay, good. Now, I mentioned 2 other genetic conditions. These are not all of the genetic conditions that provide resistance. Thalassemia is another form of anemia. Anemia just meaning not enough red blood cells. And just like sickle cell, 2 copies, people have low numbers of red blood cells, each with less hemoglobin than normal. And so they suffer from fatigue. Obviously, you don't have as much oxygen going through your body. You can't produce energy as well. Jaundice, which is a sign of liver damage, low growth rate, and bone deformities, all related to not being able to get enough oxygen around the body. People with 1 copy of the thalassemia allele are carriers with resistance to malaria, just like sickle cell.
Is it resistance or inadequate host?
Yes, both.
Okay. Yeah, cheers.
Yeah. So you can still get infected, but the parasite is not going to thrive in your body the way it would thrive if you have normal red blood cells. It's less likely to be able to reproduce. G6PD. This is a condition that affects men primarily because it's on the X chromosome. And remember, men, genetic males have an X and a Y. Genetic females have 2 X's. Usually. There are exceptions there. Again, this is largely in African Americans and people with Mediterranean ancestry or Asian. What happens with this condition? So this condition causes red blood cells to break down under certain conditions. So stress, certain medications will cause red blood cells to break down, which means you get fever, dark urine, pain, fatigue. It can also affect some of the internal organs that have a lot of blood working through them. But again, we're affecting the red blood cells. They're not surviving long enough for the parasite to reproduce. Same story over and over again with these genetic conditions. Any other questions here? Okay, grab your screenshot. Then we're going to step away from the science a little bit and go a little bit into written history. So Malaria was named during the Roman Empire. And it was named, the mal part means bad. The aria part refers to air. So it literally means bad air. Remember, in ancient Rome, they had the miasma theory. And it makes sense that they would think that bad air causes diseases. I mean, we've talked about this before. Some diseases are spread through the air, but things like malaria are caused by mosquito bites. Where are mosquitoes found? Near swamps, which generally have a strong smell. So they're thinking that what they're smelling is the disease and not just a sign that there's a lot of water around, and therefore mosquitoes and therefore malaria. So that's how we got the name malaria. Now, they didn't have good treatments. One preventative used in ancient Rome was writing special words on a piece of papyrus and wearing that on a necklace. And for malaria, that word is abracadabra. So it's a word that's still in our vocabulary today, right? Magicians, abracadabra. It was originally supposed to protect people from malaria. We don't know what the ancient Romans thought that it meant. There's a lot of ideas about this word, about where it came from, but we don't have any evidence about it. It just kind of shows up. We don't know where from. Okay. So if you want to take a screenshot. Okay. Now, malaria occurs in what we call the New World. So the New World is North, South, and Central America. There was no malaria in the New World pre-Columbus. So before the Europeans arrived, there was no malaria in the Americas. When the Europeans colonized the New World, they brought malaria in their bloodstream because at this time, malaria was widespread in Europe. And so they carried it with them in their blood and in the blood of their slaves. And now malaria is firmly established in parts of Central and South America. So, moving a little bit further forward in time into the late 1700s or mid 1700s, Jesuit missionaries in the Andes, which are the big islands along the west coast of South America, noticed that the locals I have no idea how they pronounce it. Quechua people, chewed the bark of a tree to treat fevers. This was the cinchona tree, and the bark of this tree increased the symptoms of malaria. So the Jesuits, of course, name it Jesuits bark. Not after the local people who knew about it long before. They named it after themselves. And it turns out that the bark of this tree has a molecule called quinine. Quinine is an effective anti-malarial treatment. Now, Europe had malaria at this time. So, what do you think happens?
They brought like saplings back with them, tried to grow it there so they could reproduce this medicine.
Yes, they dug up plants. They stripped the bark off of plants and carried that to Europe. They took seeds. They weren't legally supposed to do this, but they did it anyway. The local government says, no, 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 you can't take our trees. Since when did colonialists listen to the local governments, right? So eventually, the problem was these trees did not grow in Europe. A lot of times the seeds and the saplings didn't even survive the ocean voyage. But if they did, they didn't survive to be planted. But the Dutch got hold of some seeds. And instead of planting them in Europe, they took them to the Dutch colony on the island of Java, which is in Indonesia. It's a shorter trip. It's a climate much more like what the trees were used to. And the Dutch, very well known for their horticultural abilities. Even so, it took 30 years for them to develop a plantation. And they started growing cinchona tree plantations in Java and then into India. Quinine worked, but it was expensive. So only the wealthy could afford them. And this is when we start seeing malaria become a disease of poverty rather than a disease of everybody. Okay, Nate, go ahead.
Was the high cost due to the conditions it had to be grown in and also them having to transport it like back and forth?
Yeah, a lot of it was transport and the time and effort of growing the trees. Yeah.
Because that time frame, that must have been like the peak of the Dutch East India Company, right? I mean, because they were like massive traders and whatnot through that
Yep.
era.
Yep. All right, and it's time to wrap this up. We are going to talk about next time about how the cinchona tree really allowed Europeans to finally invade and colonize Africa and India, which they really could not successfully do because of malaria. All right. If there aren't any other questions, we'll wrap this up. Everybody have a good weekend.